Hello everyone and welcome to today's session on Introduction to Multivariate Techniques. I am Mrs. B. Revati, Assistant Professor in the Department of Artificial Intelligence and Data Science at Ramco Institute of Technology. In this lecture, we are going to explore how statistical techniques help us to analyze the data involving one, two, or many variables. By the end, you will understand the basic ideas behind univariate, bivariate, and multivariate methods, and also why these tools are very essential in modern data science. Let me begin with a quick overview of what we will be discussing today. First, we will revisit univariate techniques, methods used when analyzing a single variable. Next, we will move to the bivariate techniques, where two variables are studied together to understand their relationships. Finally, we will explore a range of multivariate techniques used when more than two variables come into play. These methods make up the backbone of many machine learning and statistical modeling tasks. So, having a good conceptual understanding is very important. Types of statistical techniques. Broadly, statistical techniques can be categorized based on how many variables they analyze at a time. The first one is univariate, where we focus on a single variable. The second one is bivariate, where we analyze the two variables and try to understand the relationship between them. The third is multivariate, involving three or more variables simultaneously. As we move through these categories, the level of complexity increases, but so does the amount of insight we gain from the data. Univariate analysis introduction. Let's start with univariate analysis. The word uni means one and variate indicates a variable. So here we are only studying one variable at a time. For example, the weight of college students, the marks scored in a particular subject, or the number of visitors to a website per day. The main purpose is to understand the distribution, how the values spread, where the center lies, and how much variation exists. Univariate testing mechanisms. When conducting univariate analysis, we often use several tools to describe and summarize the data. These include frequency tables to count occurrences, measures like mean, median, and mode to understand central tendency, and measures like range, variance, and standard deviation to understand the variability. Visual tools such as histograms, bar charts, or box plots are also extremely helpful because they give us a quick snapshot of how the data is shaped. All these techniques allow us to understand the behavior of one variable in depth. So additionally, univariate examples are continuations of the univariate techniques. Univariate analysis is often simplest yet one of the most important forms of univariate analysis. Before diving into relationships between variables, it's meaningful that we understand each variable independently. For example, before predicting a student's performance, we first examine the distribution of their marks. The baseline understanding helps ensure that the assumptions we make later, especially in advanced modeling, are valid and meaningful. Now, let's move on to bivariate analysis. This type of analysis deals with two variables. The main purpose is to explore whether and how the two variables are related. For example, you might study the relationship between study hours and exam scores, or the relationship between advertising spend and sales. A common measure used here is correlation, which tells us both the strength and the direction of the relationship and ranges from -1 to +1. These are the different types of bivariate analysis. There are many methods used in bivariate analysis. Correlation analysis checks the degree of linear relationship between two variables. Cross-tabulation allows to study categorical relationships. Simple linear regression helps us understand how one variable can be predicted based on another. Visual tools like scatter plots make it easier to observe how the variables move together or whether the relationship is weak, moderate, or strong. Bivariate analysis often serves as the stepping stone toward more advanced multivariate modeling. Multivariate analysis introduction. Now we enter the world of multivariate analysis where more than two variables are examined together. In the world data or the real world data, this is almost always necessary because outcomes rarely depend on just one or two factors. For example, predicting customer satisfaction may involve age, income, past purchases, website behavior, product features, and more. Multivariate analysis allows us to uncover deeper patterns, identify hidden structures, and build complex predictive models. So these are the classification of multivariate techniques. Principal component analysis or PCA is a dimensionality reduction technique. It helps us to reduce the number of variables in a data set while keeping most of the important information. PCA identifies directions called principal components that capture the maximum variance in the data. It's widely used in fields like image recognition and data compression. For factor analysis, on the other hand, aims to find underlying factors that explain the correlations among observed variables. For example, students' performance in mathematics, physics, and engineering might all be influenced by an underlying factor such as analytical ability. Factor analysis helps uncover these hidden structures. So, other multivariate techniques are there are several other important multivariate techniques involved in the introduction. Multivariate regression analysis predicts an outcome using multivariate independent variables. MANOVA or multivariate analysis of variance examines group differences across several dependent variables simultaneously. Canonical correlation analysis studies the relationship between two sets of variables. Logistic regression is used when the dependent variable is categorical, such as predicting whether a student will pass or fail. These tools allows us to answer more complex questions compared to univariate or bivariate methods. Some additional multivariate techniques include conjoint analysis, which is used extensively in marketing to understand customer preferences. Customer analysis groups data points based on similarity and is widely used in customer segmentation, image classification, and pattern recognition. Multidimensional scaling helps visualize instances or similarities between items, is often used in psychology and market research. Structural equation modeling or SEM is a powerful method for studying complex cause and effect relationships. Confirmatory factor analysis or CFA is used to test whether the data fits a hypothesized factor structure. Together, these techniques give analysis a wide toolkit for handling multidimensional datasets. Next, we move on to the multivariate discriminant or multiple discriminant analysis and canonical correlation analysis. Multiple discriminant analysis helps classify the data into groups based on several predictor variables. For example, it may help categorize customers into high value, medium value, and low value groups based on their demographic and behavioral characteristics. Canonical correlation analysis, meanwhile, examines the relationship between two sets of variables, for instance, understanding how students' academic behaviors relate to their learning outcomes. So, both these techniques are highly valuable when dealing with complex multidimensional data environments. Next one is conjoint and cluster analysis. Here, the focus is on two widely used applied techniques. Conjoint analysis helps organizations understand what combinations of product features customers value the most. This method is essential in designing new products or setting competitive pricing strategies. Cluster analysis groups individuals or items based on the similarities without any predefined labels. It's extremely powerful in identifying natural segments in data such as customer types, product categories, and biological classifications. We have now reached the end of our session. Today, we moved from simple univariate analysis to the more complex world of multivariate techniques. These methods form the foundation for much of the work done in data science, machine learning, and statistical modeling. I hope this session has given you a clear conceptual understanding of the various techniques and their real world applications. Thank you for joining me, and I encourage you to explore these topics further through hands on practice and deeper study. Thank you.